Okay, this video is on domain of functions in their equation form. This is usually pretty tough for students, so I've broken it up to kind of give you an idea about domain and how to do it in different types of situations. First step I'm going to look at is the linear function, so lines. So if you have a straight line, as we can see that this one is a straight line, f of x equals 2x plus 1. This is the graph of it, and you can see that it goes from the far left all the way down here and keeps going up and to the right. Now remember, the domain are the x values. So if I'm looking at the x-axis here, 4, 3, 2, 1, 0, -1, -2, -3, -4, you can see that all of those values are used. Every value on the x-axis, all of these values right here, have a point on this line. So if I go up there with the marker here, and I can show you that -4 has a point. It's way up here. See, right? That's in line. Or sorry, +4. +3 has a point right there. 2 has a point right there. 1 has a point. 0 has a point. That one has a point for x, right? I'm looking at all of them. Actually, I can look at every point on the x-axis. It doesn't have to be just -2, -3. They're all on the value. So there you go. So you can see that every x, no matter where you put your pen on this line, if I put it here, can I go up to the line? Yes. 2.5? Yes, see? You can see that the line covers the entire x-axis. Every value on the x-axis will have a point on this line. I'll have an x and y value, right? That's what I mean by having a point. So there's a y corresponding with this input. Now, how do you see it from here? Well, let's look at that one. By looking at it, can you put any x value in here and get out a y value? So, for example, if I put 2, which is right here, put 2 in, should give me 5 out, right? Because that's the point 2, 5. So I put in 2. 2 times, this is where the 2 goes, 2. 4 plus 1. See, I get 5. I get that 2, 5 out. So that's showing me that, yeah, if I put 2 in, I get 5 out. That's a point on the line, so 2 is in the domain. Now you can do that for all of them, though. That's the whole idea. It doesn't matter what x value you put in here, you're going to get a y value out. Okay? Now, you can't find any x value in the entire whole line that won't give you something out, right? Because 2 times a number plus a number is another number. So that's what we mean by the domain of this function is all real numbers. So we say all real numbers for the domain, like that. Or you can actually say all real numbers, right? All real numbers. Okay? There's other ways of writing that. The more correct way, let me erase some of this here, would be in the set notation. So all x such that x is a real number. Okay, so that's another way to write it. What else? I think that's about it for this one. So there are no problems. That's what I mean by when I say there are no problems with any number, because you can multiply it by 2 and get out and add 1 and get out another number. So there's no problems with this function, and there's no problems with any line. No, every line will always be all real numbers except if it's a vertical line, right? Because it's not even a function. Okay, moving on. Polynomials. If we move on to now polynomials, polynomials are just functions that are written out this way, descending order of the powers, right? And there again, there are no problems. If we look at the graph, this is the graph of this polynomial. You'll notice that it just continues up, and no matter what x value you choose again, if I choose any x value along this line, let's just choose, I don't know, 3. I choose 3, I go up, yes, look at right there, there's a point on the line. Okay, I can choose any other one. It doesn't even matter. If I choose -1, is there a point on the line at -1? Yes. Again, this is because if you put -1 in here, you're going to get out a value. Can you see that? -1, -1 cubed, minus -1 squared, minus 4 times -1 plus 4. Alright, and any value you put in there, you're going to get something out. So the domain, again, are the values you're putting into this function. So, again, I can put all real numbers. The domain of this function is all real numbers. The domain of all polynomials is all real numbers because there are no problems. It will span the entire graph here. Entire graph, it'll span that whole thing. Meaning every x will have a corresponding y. So with linear functions, they're all real numbers. Polynomials, they're all real numbers. Let's move on to the next one. Root functions. So here I have a square root. Now we have to be a little careful because look at my graph. My graph starts at -4 in because with square roots we can't take, say, the square root of negative, say, 9, right? What is the square root of negative 9? It's an imaginary number. So I can't put a square root into or I can't put a negative number into a square root function. But you got to be careful what's under here. Look at x plus 4. So it allows me to put some negative numbers in for x that will produce a positive number. So for example, if I put -4 in for x, right? So -4 in for x, like this, square root of -4 plus 4. See, there's my -4, there's my plus 4. This equals square root of 0, but the square root of 0 is 0, and that's why we have that point right there. -4 in, 0 out. But if I were to try to put, say, -5 in, this would be -5, square root of -5 plus 4, which equals the square root of -1. Well, we have a problem now, see? We don't know the square root of -1, just like I didn't know the square root of -9. So how we find out the domain of square root functions is that we take what's ever under the square root. So let's see here. The x plus 4 is under the square root function, see right there. And we need this to always be greater than or equal to 0. Okay? Because you can't take a square root of a negative number. So we want this to always be greater than or equal to 0. Alright, now we just solve that equation. So I subtract 4, I have x is greater than or equal to -4, and that would be the domain of a square root function, meaning you can choose any x that is greater than or equal to -4. And look at my graph. It starts here. It starts here at -4. And it goes all the way, so if I highlight from -4 all the way over, and it continues going on right off the page, right? But if you look to the left, there's no red lines. There's no part of this graph over here on the left. And that's because you can't put in -5 into here and get a number out. So by looking at this function right here, what we say is we take whatever underneath there, set it greater than or equal to 0 and solve it. And then that's our domain. All even functions, now this is an even square root, all even functions follow the same way. Now if we move on to the odd function, it's a little different. Because now when you have odd, you can see, look at the graph immediately, it looks very similar, doesn't it? But look at, there's also something to the left. And that's because you can take cubic roots of negative numbers. So let's go ahead and put in -1. Or sorry, not -1, -5. Let's put in -5 into this function, and we'll see that we get the cubic root this time of -5 plus 4. -5 plus 4 is -1. Remember last time I had a square root of -1. I couldn't do it. But the cubed root of -1? What number times itself 3 times is -1? -1. There's that point. -5, -1. So it exists. So you can see again, just like my linear functions, just like my polynomials, it spans the entire graph. Every x value, no matter what you choose here, will have a point on this line. You'll have a y value that comes out, and you can put a point on there. So all odd roots, see that's an odd, that cubic, all odd roots are all real numbers. So our answer here, all real numbers for the domain. But remember, go back up here, it's not all real numbers. It's restricted by what's ever under here. You must keep this positive. You must keep it greater than or equal to 0. Alright, my last one is rational functions. Rational functions are fractions. That's what rational means. It means fractions. So here I have a fraction. Now remember, A long time ago you learned that you can't divide by 0. You can't take, say, one thing and divide it into 0 groups. This is always what we say undefined. Okay? So that's where the problems occur with the domain here. Remember, domain are the x values that you are choosing to put into the function. You can't have the denominator to be equal to 0. So I look down here and I see that this denominator is x squared minus 16. So what I'm going to do is just factor it. So let's write it over here. R of x equals x minus 2 over, that's a difference of squares, right? X minus 4, x plus 4. Okay. Now this is the same function. All I did is just factor the denominator. Now you can see that in the denominator there's x minus 4 and x plus 4, so we know that if we have x equals to 4 or x equals to negative 4, we have some problems, right? Because if I put 4 into this function, right, watch, r of 4, I get 4 minus 2, that's fine, but look down here, 4 minus 4, 4 plus 4. What's 4 minus 4? That's 0. What's 0 times 8? 0. This is what I'm looking at. That's a problem. We can't have this, right? Okay, so that means that 4 cannot be put into this function. And you look on the graph, look down here. There's a little dotted line here. What this is called a vertical asymptote. You will see that this is the graph. You might not be familiar with this, but this is the graph of this rational function. And you can see that this red line goes up and up and up and up and up, but it never actually touches that dotted line. See, the dotted line is a little bit to the left of that still. And then here, this part of the graph goes down and down and down and never touches the dotted line. That's because 4 never produces a number, but everything else will. So you can see the entire graph, everything produces a number except 4 and negative 4. So there's no part of that graph. That dotted line just shows you that that's called a vertical asymptote and that these lines go towards it forever. So by looking at the function here, though, you can immediately say, oh, I can't have numbers that go into this function that make the denominator 0. So I factor it, see the two numbers, and then I can write the answer. So the domain would be, written out like this, would be all real numbers, you can say, but x cannot equal negative 4 or positive 4. Or, all notation, the subset notation, all x such that x does not equal negative 4 or positive 4. Okay, we're saying that it's all these values from here all the way to negative 4. Stop. Start up again. All the way over to positive 4. Stop. Start up again. All the way to infinity. Right? It's from negative infinity all the way there, but not including those two. So that's what we're writing here. All values but negative 4 or positive 4. Interval notation, some of you like to see that. It would be written like this. Let me erase a little spot here. Interval notation from negative infinity to negative 4, not including negative 4, union with negative 4 to positive 4, not including positive 4 or negative 4, union with 4 to infinity. So that's kind of a long way to write it out, right? So, there's multiple ways of writing this problem out. But that's with rational functions now, remember. Those are rational functions that have numerator, denominator. They are fractions. Always look to the denominator, exclude the values that make it equal to 0.